Hi, it's Dr. Z. In this video, I will introduce the concept of one-tailed hypothesis tests. By the end of this video, you'll be able to explain the difference between one-tailed and two-tailed tests. You'll also be able to conduct a one-tailed hypothesis test using a z-score for a single score x. Please feel free to pause the video at any time to take notes on the chapter handout. Recall that hypothesis is just a fancy word for prediction. In a two-tailed hypothesis test, your prediction is that you don't know how the treatment or the independent variable will impact the sample. On the other hand, a one-tailed hypothesis test is predicting that you do know how the treatment or independent variable will impact the sample. A two-tailed test is the first hypothesis test that you learned how to do. This test uses a non-directional hypothesis. The prefix non means not or unknown. In other words, we do not know in what direction the sample will go. The treatment given to the sample may increase or decrease the sample score. We use a non-directional hypothesis when we do not know how the treatment will impact the sample. The two-tailed test is the most common test used, especially when conducting new research. The null and the research hypotheses will be the same as in the previous lecture video. If it's not obvious yet, the critical region for this test will be in both tails, since we do not know which direction the effect will be. On the other hand, a one-tailed test uses a directional hypothesis. The root word direction implies that we have an idea of which direction the treatment or the independent variable will impact the sample. The hypothesis will specify either an increase or a decrease in the sample score. You should see the pattern now that the critical region for this test will be in one tail, as specified by the directional hypotheses. This diagram illustrates the process of hypothesis testing. We will use the same 4 steps in conducting a one-tailed hypothesis test, well, with some modifications along the way. Step 1, the yellow Lego, is to state hypotheses. Since we are using directional hypotheses instead of non-directional, we will have our first modifications in this step. Writing directional hypotheses are especially confusing to students. To make them easier, it is extremely important that you write the research hypothesis first. Then, the null hypothesis will be easier to write afterward. Recall that the research hypothesis is predicting that a difference will happen. In a directional hypothesis, we are predicting that we know in which direction this difference will happen. The research hypothesis would be written like this. The sample that receives the independent variable will have an increase or decrease on the dependent variable compared to the population who did not. Recall that the dependent variable is what is being measured in the study. The independent variable is being manipulated by the researcher. You will need to fill in what the independent and dependent variables are in the hypothesis statement. Since we are predicting the direction, you will fill in whether it's an increase or a decrease. Please note that the words sample and population are in bold. This is to remind you how important it is that you clearly state that a sample is being compared to a population. You will also need to write the research hypothesis in notation. We will use the same notation as a two-tailed test. The notation for population mean, which is mu, and the prefix tx for treatment, where you will replace the tx with the name of the treatment or the independent variable that was given to the sample. For a directional research hypothesis, there will be 2 options based on the direction that is hypothesized. The first notation predicts that there will be an increase. If we were to translate the notation into words, it would say if we could give the entire population the treatment that the sample received and the increase in direction we predict happens, then the treated population is greater than the value of the population mean. Notice that we're using the greater than sign to indicate the increase. The second notation predicts that there will be a decrease. If we were to translate this notation into words, it would say, if we could give the entire population the treatment that the sample received, and the decrease in direction we predicted happens, then the treated population is less than the value of the population mean. Note again that we're using the less than sign here to indicate the decrease. Writing the directional version of the research hypothesis is the hard part. Once that is written, the null hypothesis is much simpler. Recall that the null hypothesis is predicting that nothing will happen. In a directional null hypothesis, you are saying that there will not be an increase or decrease as specified from the research hypothesis. You will simply add the word not into the null hypothesis statement. For notation, the null hypothesis will reflect that there was not the predicted decrease or increase. In fact, it'll be the opposite of the prediction. For a directional null hypothesis, there will be two options. The first notation is predicting that there will not be an increase. If we are predicting that there is not an increase, the sign will be equal to or less than the value of mu. If the sample is the same value as mu, meaning they're equal to each other, then that is still not an increase. That is why we're using the sign equal to or less than in notation. In essence, the sign here in the null hypothesis is the opposite of the sign used in the research hypothesis. The second notation is predicting that there will not be a decrease. So if we're predicting that there is not a decrease, the sign will be equal to or greater than the value of mu. If the sample is the same value as mu, meaning they're equal to each other, that's still not a decrease. That is why we're using the sign equal to or greater than here in notation. The concept of writing directional hypothesis statements may be difficult to understand right now. The lecture example at the end of the video will provide clarification. Step 2, the blue Lego, is to set the criteria to make a decision whether the study worked or not. First, we will set our significance level P. We will use either a 0.05 or a 0.01 significance level. Now that we know our P, we need to find the critical value or critical region that tells us what the sample should look like if the study worked. We will use P and the normal curve table to find the corresponding z-score, but for one tail only. The next slide will demonstrate why the critical region for a 0.05 significance level is always z equals plus 1.64 or z equals negative 1.64, one-tailed. Let's graph what the critical region Z would look like. Using the normal distribution, where will the one outlier be located? Well, since it's a directional hypothesis, it could either be in one tail or the other tail. So either above the mean or below the mean. The significance level of 0.05 refers to 5%. Since we're only using one tail, the 5% stays in one tail. You will go to the normal curve table, look in the tail column for 5%. Once you find the 5%, the normal curve table states that the corresponding z-score is 1.64. If the hypothesis is predicting an increase, then the critical region would be a plus 1.64. Now, if the hypothesis is predicting a decrease, then the critical region would be a negative 1.64. You must clearly state whether the critical region is a positive or a negative to accurately reflect the direction of your hypothesis. If you give me both critical regions, positive and negative, it will be marked incorrect because it shows me that you don't know which direction you are hypothesizing. I encourage you to pause the video and look this up yourself in the normal curve table. Step 3, the red Lego, is to collect data and calculate sample statistics. Fortunately, this step stays the same as it would for a two-tailed test. You will calculate the z-score for the sample using the formula provided in an earlier lecture video for a two-tailed hypothesis test. Step 4, the green Lego, is to make a decision about whether the study worked or not. This step also stays the same as it would for a two-tailed hypothesis test. If you need a review of the two decisions in hypothesis testing, please see an earlier lecture video for an explanation. Now that we reviewed the steps of a one-tailed hypothesis test, are you ready to practice your new knowledge? I have one lecture example for you to review. First, in your chapter handout, there is a list of steps. This is a short summary of the 4 steps that we described earlier in this video. Please note that these steps are for a one-tailed hypothesis test using z-scores. There are 2 modifications noted in bold. Please pause the video to write down these steps on the chapter handout. This lecture example wants to know if blueberry supplements can improve cognitive function. The word improve implies that we're predicting an increase in cognitive function. In other words, we will be using a directional hypothesis. The details of this research study are provided in your chapter handout. This research study is giving blueberry supplements to the sample. The supplement is the independent variable, which is being manipulated by the researcher. Cognitive function is being measured to determine if the supplements worked. Cognitive function is the dependent variable. In this example, we know that the adult population scores a specific way on a cognitive test. Since we cannot study the entire adult population, we have one patient that takes blueberry supplements for 6 months. Then we will compare this one patient's score to the population to see if the direction of our prediction was correct. I encourage you to pause the video here and try to do the 4 steps on your own first for the lecture example. Then resume the video to show the answers. Step 1. Since we're predicting that there will be an increase in cognitive function, the research hypothesis will reflect that wording. The words cognitive function are underlined because it is the dependent variable, and the blueberry supplement are underlined because it's the independent variable. Since the treatment in the study was blueberry supplement, I shorten it to BBS. The word increase is in bold to reflect that we are predicting an increase in cognitive function. In notation, mu BBS is greater than 80. In other words, if we could treat the entire population with blueberry supplement and the increase that we predicted happened, then the treated population should be greater than, note the sign, than the population mean. In the lecture example, the population mean is mu equals 80, so we will place the numerical value of the population mean in the notation. For the null hypothesis, the wording will reflect that there was not an increase. And in notation, mu BBS is less than or equal to 80. Meaning that if we could treat the entire population with blueberry supplement and there was not an increase, then the treated population should be equal to the population mean or less than the population mean. Again, the sign in the null hypothesis is the opposite of the sign in the research hypothesis. Step 2. As a researcher, we get to decide the significance level, and the preferred one is 0.05. Since we are predicting an increase in cognitive functioning, we need to draw a critical region Z for one tail, for above the mean. The corresponding Z-score for a 0.05 significance level one-tailed is Z equals plus 1.64. The box indicates the final answer that I will be looking for on problem sets and exams. Step 3. This step is the same as for a two-tailed test. We will use the modified Z-score formula that allows us to compare our sample X-score with mu and sigma. Using the formula, we will plug in the values for X, mu, and sigma that are given to us in the lecture example. The Z-score for the one patient who took blueberry supplement is Z equals plus 1.75. The box indicates the final answer that I will be looking for on problem sets and exams. Now, I want you to think like a researcher. What does this Z equal plus 1.75 mean? The plus sign indicates that it's above the mean or that there was an increase. Our dependent variable, or the variable that we are measuring, was cognitive function. So this Z-score means that blueberry supplements appear to increase cognitive function. This initial interpretation of the Z-score value is critical in writing summary and interpretation statements. Step 4. Now we need to make a decision to determine whether the study worked or not. In this step, we will compare the sample Z-score calculated in step 3 to the population prediction determined in step 2. In other words, does the Z of plus 1.75 that we calculated in step 3 fall in the critical region Z from step 2? Using the graph, we can see that the plus 1.75 falls in the tail just past a Z of 1.64, meaning the answer is yes, it does fall in the critical region. Then the decision is to reject the null hypothesis. The box indicates the final answer that I will be looking for on problem sets and exams. Thinking like a researcher, though, what does it mean to reject the null hypothesis? This decision means that the study appears to be statistically significant. Again, this initial interpretation of the decision is critical in writing summary and interpretation statements. After a hypothesis test is conducted, the researcher must report and interpret the results of the study. You will watch an additional lecture video that reviews how to write the summary and interpretation statements for this specific lecture example. In summary, researchers use a directional hypothesis when they have an idea of which direction the treatment will impact the sample. Then researchers conduct a one-tailed hypothesis test to determine the results of the study. Learning how to conduct a one-tailed hypothesis test is one more major Lego building block needed to understand statistics.